Hi, everyone, and this will be our Friday lecture for Friday, December, February 26th. I looked and it said 25th. That's today. 26th is tomorrow. Don't worry about it. It's been a long day. Friday, February 26th. We are going to introduce friction as our last specific force that we're going to work with. Solve a few problems with friction, and then have kind of a short lecture just about friction. That'll be the end of today's class lecture. I'm also going to record a little bit of a longer lecture where I will work through 3, 4 more complex problems so you can see all of the tactics and approaches that we've been using over the last week and a half in the most context-rich problems that we will typically see. So, if we think about friction and what friction is, let me resize this window. I know I shouldn't be doing this live, but I just see that I want it a little bit different. There we go. I like that a little better, I think. Friction is a retarding force that always works against the motion of an object, or what would be the motion of an object if the object is standing still. For instance, take for example this person pushing on this large crate. There exists the possibility that they push to the side and the crate doesn't move, right? This person is pushing to the side with a pushing force. There is no movement of the crate. So if we were to draw the force diagram, whoops, I realize that's where my picture is. There we go. We know that they are pushing to the side with a pushing force. There is the normal force and the weight force. Again, these diagrams that I've stolen from another textbook use things like W for weight and N for normal force. We'll use our textbook's symbol structure, Fn and Fg. But obviously, if they're pushing to the right and the box is not moving, we can think about Newton's second law and say, if the box is not moving, the acceleration must be 0, and therefore the net force must be 0. So there has to be this force working against their push in the case of the box staying still, being static. We call that a static friction force. So a friction force, F of S, that is a static friction force. Or here I said FS, a force of friction static. That's how I've written that. This is a force that is kind of a little bit interesting in that it can change its size. By that, we can think about the examples here where we're pushing gently on the box, and we see that the static friction force matches because, again, it only has to be as big as the push so that the force is 0, the net force is 0 if the box doesn't move. If we push harder and the box doesn't move, then the static friction force actually got bigger to match our push. And then if we push hard enough to just get the box to start moving, we actually reach what's called the maximum static friction force, the maximum static friction force, which is that breaking point where the box is just going to begin to move. That'll be the maximum force possible from this static friction. Now, what determines the friction force? There's two things that determine whether or not a box is going to have a friction, how big the friction force is going to be for this box that this person is pushing against. One is, if we think about this diagram again, this cartoon, we have the force of contact, this normal force, contributing to the friction force, and we also have the surface here. Whatever the surface is going to determine how difficult it is to move that box. Again, here's a little thought experiment that we can do. If you are trying to move the box and a person says, oh, that box looks heavy or difficult for you to move, let me take all the stuff out of the box. Well, the box is lighter now, which reduces that force of contact between the box and the floor, and that makes the box easier to move. That's going to reduce this friction force that you were up against in terms of how hard it was to move the box. Similarly, the surface matters. If the box is hard to move, someone could say, oh, let me squirt some oil or some other lubricant on the floor. Now that surface is slippery and the box is easier to move. So the friction force actually depends on two things. And down here we have one statement of the friction force. Again, this is from a different textbook. So we will see this as F, the force of friction static, is equal to mu times the normal force. This mu, this Greek symbol mu, is the coefficient of friction. That is a value that determines what surfaces, or I should say is determined by what surfaces we have in our system. So different combinations of surfaces have different coefficients of friction. Your textbook has a table that specifies different frictions. So if I have rubber on pavement, if I have wood on glass, if I have whatever the combination is, it'll give us the coefficient that determines how slippery of a surface interaction there is from one surface sliding on another. The other thing that matters, of course, is the normal force, how firmly those surfaces are pressed together. Now, friction is also important when things are moving and sliding. So if we have a case where we are now pushing on a box and it is moving, we have to push against this kinetic friction force. So if I have, and in these two examples, the box moving at a constant velocity, so both of these are constant velocity, we see again that the pushing force and the kinetic friction force are matched. It does not matter whether we're moving fast or slow. Constant velocity is still acceleration of zero, but we are pushing and we're not accelerating, right? If it was just our pushing force, if we only had this pushing force, we would have a net force to the right and our box would be accelerating. Our crate would be moving faster and faster and faster. We know from everyday experience that I can push. I mean, imagine you're moving a couch, right? You're sliding furniture across your living room. You're pushing and exerting a force, but it's probably only moving at a constant velocity once it starts moving. That's because there is a friction force acting against your pushing force, which allows there to be a net force of zero. Now, again, this friction force depends on two things. It depends on the normal force of contact, how firmly those objects are pressing together. So how much is the floor pressing up on my crate? And it also is determined by the surfaces at play, right? Is it a wood box sliding across a very rough floor, or is it a wood box sliding across a floor with a soapy film on it? Those surfaces are going to give different coefficients, which might reduce or increase the friction force, right? A very slippery floor will have a low coefficient of friction. A very rough floor and interacting with that surface of the box will have a large coefficient of friction. Some words on the coefficient of friction itself. Those of us in lab, we've already seen this a little bit, but mu is a number between 0 and 1.00. 000. I mean, there's no limit to decimal places, but between 0 and 1. So it's always a positive decimal value. If I ever have a mu that's negative or a mu that's greater than 1, I've made some mistake in my problem solving, in my algebra probably. It's always a decimal number, a positive decimal number. The stickier, right, so smaller mu's, we'll say that that's slippery. and larger mu's we'll say it's stickier, right? It's a rougher, maybe that's a better word, right? It's harder to slide across that surface. Think about you take your car keys and you slide them across the parking lot. They only go so far, right? Because it's metal keys on rough pavement. They might, if you try to slide them, it might go, I don't know, a meter or so before they slow to a stop. Now, 2 weeks ago, when there was that layer of ice over the parking lot, you let go of your keys and they slide all the way down the parking lot because the coefficient of friction is very little, very small. So there is nothing slowing down your keys, nothing acting on those keys with a negative net force and therefore a negative acceleration, causing them to slow down. Just a little thought experiment you can perform. Let's work a few simple problems with coefficient of friction and the friction force, just to introduce this idea. So let's say that we've measured with a force meter, some kind of spring scale that we have, that we need a 16 Newton force to move a potted plant across our patio at a slow speed, a half of a meter per second. We know the mass of the potted plant. What's the coefficient of the kinetic friction between the potted plant and the patio? The pot and the patio. Now, just like we've been talking about in class, we're going to solve this problem the exact same way. We are going to start with a force diagram, start with Newton's second law, applied to that force diagram, and then solve for the thing we're looking for. So let's draw a force diagram. Make sure I'm still in here. So we have our force diagram, might look something like this. We have a pushing force to the side. I gotta sit straight so my arrows are straight. And we have a friction force. Now we are moving, so we're going to use kinetic friction. Whenever we are staying still, we have static friction. Most of our problems will be kinetic friction problems, but whenever something is staying still on another surface, that's when we'll have to worry about static friction. And then this pot, of course, has a weight force down. So there's the gravitational force. And then it has a normal force up. Now, in our last class on Wednesday, I said we're always going to consider both dimensions, even if the problem doesn't need both dimensions. Well, now when we have friction, we'll see a pattern in that we will always need both dimensions to be considered. Here's what I mean by that. If we write the Newton's second law expression in the x direction, we have the sum of forces in the x direction, our net force, is equal to mass times acceleration. Now the sum of forces in the x direction, that's going to be our pushing force to the right minus our force of friction, kinetic, to the left. Sum of forces, but to the left is where we get that negative sign. And now if we look back at our definition of kinetic friction, our pushing force minus, we can write the kinetic friction as mu times the normal force is m times a. Now for our problem here, we can start substituting in some stuff. We have a constant speed, so that means our acceleration is 0, right? This is 0, so that whole side is 0. And we want to know the coefficient, right? We're starting with an easy problem where we just want to know the coefficient, but we don't know the normal force. Now, here's where we have to be careful. If we've been doing the homework, if we've been solving a few problems, we might jump ahead and say the normal force is equal to mass times gravity. The normal force is equal to the weight. In this problem, it is. In this problem, that's true. Let's be explicit about it, though, and we'll see in the next problem why. Let's consider the y direction. Well, that's a highlighter. Ha ha ha. Erase that. Don't pay attention. Here we go. In the y direction, the sum of forces in the y direction, the y component of the net force, is equal to mass times the acceleration in the y direction. I mean, this we could put an x over here, mass times acceleration in the x direction. Sum of forces in the y direction, we have the normal force minus the gravitational force. And in the y direction, if this pot is just, let's draw a little cartoon, right? This pot is just moving horizontally. There's no acceleration in the y direction. That equals 0. Therefore, the normal force is equal to the gravitational force, which is mass times gravity. Okay, because we've determined that, here we have, now we can go back to the x equation, the pushing force minus mu times the normal force. We'll substitute in what we found in the y direction, where we were told that the normal force is equal to mg. So here we have doing a little bit of algebra, and I'm just kind of doing a few steps in one. Make sure you're following along what we're doing here. If you need to stop and work some of the algebra yourself, that's fine. 16 newtons over a 3 kilogram mass times 9.8 meters per second squared gives us, sorry for not calculating this ahead of time, 16 newtons divided by 3 times 9.8, being careful with my parentheses, 0.544. So we get a positive value. It's less than 1, a decimal value. Perfect. The next problem we're going to do is going to emphasize this important point of we can't always say that the normal force is equal to the gravitational force. I mentioned something in class about a kid's book that said that. I'm gonna pause the video and I'm gonna go grab that. I'm gonna sneak into my sleeping son's room and steal it off of his bookshelf. I'll be right back. So this was the book I mentioned in class. Again, the next problem is going to tear this book apart. This book is called Newtonian Physics for Babies. It's kind of a tongue-in-cheek kid's baby book about this is a ball. This ball feels the force of gravity. And look, they have a force diagram, okay? And it goes through all these things about this ball accelerates, this ball feels. Oh, so here's the start of it. But it also feels the force of the ground. The force of the ground equals the force of gravity. In this context, I have no problem with that because that's true. That's like the problem we just solved. In the y direction, this was true. However, it goes on to talk about things accelerating and falling. So the net force is 0. It does not change its motion. So far, we're good. Ooh, this ball has a net force. It's falling. So this ball accelerates. Now, blah, blah, blah. We do a little bit more mass, less mass, more mass, more force, less mass, less force. I got no problems with this until, out of nowhere, he says this. The force of the ground always equals the force of gravity. Let's see how easy it is to blow that out of the water. Let's assume that we have the following scenario. Let me not minimize this, but shrink this so you can see it. Okay. We've got a wooden box with a mass of 22 kilograms, pulled at a constant speed with a rope that makes an angle of 25 degrees with a wooden floor. Let's draw a quick cartoon. We have a wooden floor, a wooden box. The materials will become important in a little bit. And then we're pulling it with a rope at an angle of 25 degrees. Right? Here's someone pulling on this rope. Ugh, they're working really hard. Okay. Let's draw a force diagram. We have, I'm going to zoom in a little bit. There we go. We have a downward force that's equal to the weight. We have a tension force That's up at an angle. We want that angle to be 25 degrees. So let's draw that a little bit closer to 25 degrees. Maybe like that. So that's a force of tension, or the force of the rope. Now, what we know is that in the y direction, we don't expect this box to lift off the floor. So if the box maintains contact with the floor, we know that I already have a y component of my tension force here. My normal force does not need to be that large because it also has the y component of the tension force to help reduce that contact with the floor, right? If I'm lifting up on the box a little bit by that rope being up at an angle, I can increase that angle and start to lift the front of the box off the floor, can't I? So that tension force reduces that contact force. So we also have a friction force. The box is moving, so it's the kinetic friction force to the left. There's my complete force diagram. Now, if I want to write my equations, the sum of forces in the x direction equals mass times acceleration in the x direction. Well, my sum of forces in the x direction are let's color code here. I have the x component of the tension, Ftx, and we also have the y component of the tension, Fty. Since tension is at an angle, our coordinate system, maybe we can be a bit more explicit about it, is our usual x to the right, y up coordinate system. So I have x and y components for that tension force. I must break every force at an angle in my coordinate system into x and y components. So I have here for my x direction, one of my forces in the positive x direction is F tension, the x component of that. And then in the negative x direction, I have the force of friction, kinetic friction, FFK. That equals mass times the acceleration in the x direction, only because in this problem, again, we were told that we have a constant speed. We'll deal with friction and acceleration in a little bit, but we're just stressing the friction part of the friction problems, not necessarily the acceleration part. This is going to be 0, right, because we were told our acceleration was 0. If I were to be asking for, what am I even asked for here? The tension in the rope, right? So I have Ftx equal minus mu times the normal force, which equals 0. This tension force here, the x component is Ft times cosine of theta minus mu times the normal force equals 0. So I've got this expression here, but if I'm solving for the tension force, I'm not done yet, am I? I need to find another expression for the normal force, because right here, I technically have one equation and two unknowns. Whenever we deal with friction, we always consider what's going on in the y direction. So in the y direction, for this same force diagram, so I'm just going to, I want to do this. I'm going to copy that so I can go to a new page, and I'm going to paste it. Oops. There we go. So there's the force diagram that we had a moment ago. Now let's write an equation in the y direction. In the y direction, right, we still have the sum of forces in the y direction equals the mass times the acceleration in the y direction. If this box is sliding horizontally on the floor, we know that AY is equal to 0 as well. AY is equal to 0 because it's not moving in the y direction at all. AX was equal to 0 because it was moving at a constant speed. Make sure we can keep those straight conceptually. In the y direction, though, 1, 2, 3 forces in the y direction. How fascinating. Very different than the previous problem. So here in the y direction, I've got a normal force plus Fty minus Fg equals mass times acceleration in the y direction, which is equal to 0 for this particular problem. So I have my normal force plus the FTY would be FT sine of theta minus FG, which I'm just going to write mg, right? Anytime I have f of g by itself, I can write mass times gravity equals 0. So my normal force is equal to mg minus ft sine of 0. And again, take a moment to think about this equation not just as a collection of symbols, but as something with some physical meaning, right? Without that rope pulling up a little bit, the normal force is the gravitational force. But that rope being up at an angle reduces minus ft sine theta, reduces that force of contact. That means that there's less friction holding back on my object. If you think about when you move furniture, you have a heavy desk or a heavy table to move, you probably don't just push it to the side, you lift it up a little bit and then push it. You probably don't lift it up off of the floor. You might only even lift one end up off the floor and the other end is still on. Or even if it's like a big heavy couch, you might lift up but not actually have the feet of the couch leave the carpet. All you're doing is reducing that normal force of contact so as to reduce the friction, since the friction force we had on our last slide is mu times the normal force. The smaller the normal force is, the smaller the friction force, the easier it is to move that horizontally against that force of friction. So there's a little bit of a reality context here as well. Now that we have this normal force, Fn equals mg minus the force of tension, we can go back to our previous equation, which was ft cosine theta minus mu Fn equals 0. Okay, so from the x, we had ft cosine theta minus mu Fn equals 0. So now I just make a substitution. Mu for Fn, I have mg minus ft sine of theta equals 0, right? I'm just putting in this in for f of n. Simplifying a little bit, ft cosine theta minus mu mg plus ft mu times sine of theta. Erase that. Ft mu sine of theta equals 0. Be careful distributing this through, right? Minus minus gives me my plus. Some algebra review perhaps for some of us. So I have ft cosine theta plus mu sine theta equals mu mg. And there's a few more steps to solve. I'll let you do that on your own. You should get that the force of tension is equal to, I'm going to pause to calculate and double check my work. I get, when I solved it, 80.2 newtons. Now, one thing I didn't mention, because we just started working with the force diagram and Newton's second law, et cetera, when you are calculating it, you might say, well, where did you get the coefficient from? It wasn't stated in the problem. Well, the problem did state wood on wood. And in our textbook, there is a table here, table 4.2, coefficients of friction. And the first one in there is wood on wood. So for a wood surface sliding over another wood surface, we have a given coefficient from the textbook of 0.4. That's only really going to come up in the homework where they might do that. I don't even think I've assigned a problem. If I do and you don't have access to the textbook, let me know. I'll give you the coefficient. Most of the time it's stated in the problem. This one it wasn't. Normally I remember to mention that when we start the problem. Here I'm mentioning it at the end of the problem. Good. And I realize now when I held up the book that this problem proved wrong. I forgot to maximize my window. So I'll show you once more the lies that I had my kid read, and then I had to say it enough times that now my Sun says, well, that's not always true. The force of the ground always equals the force of the gravity. Lies. Because we just had a problem where the force of the ground, the normal force, was equal to the weight, force of gravity, minus the force of tension times sine theta. So this is not always true. It's true for these two spheres, but it's not always true. So be careful. What is always something, give me small again, there we go. What is always something that we're going to do is we are always going to consider the y direction to determine what the normal force is in order to talk about friction in the x direction, because that's typically the direction that friction is typically in the x direction because we pick the x direction to be in the direction of our acceleration most times, or the direction of our motion when we have no acceleration. Okay. The last thing I want to work with here is this problem here that deals with putting a book on a board and then increasing the angle of the board until the book begins to slip. We want to find the angle where it slips. I want to show you what this problem is talking about. We're just going to work this first part here, and then in class we'll start with this as a refresher. On Monday, I'm going to post some additional problems that you can look at over the weekend. But we're going to end the lecture with this. I want to make sure we can all visualize what's going on here. So again, here's a zoomed up version of me. Let's say we have here, instead of a board, we have this cutting board. Let me move my microphone out of the way so I don't keep hitting it. And instead of a book, this is just the base that my stylus rests in. But right on a flat surface, it stays there. And now when I angle it up, friction is what's holding it in place. Its weight is acting straight down, but a component of the weight is acting along the incline. Another component is acting perpendicular to the surface. There's a normal force and a static friction force there that gets bigger as we increase the incline. Now we get to a point where we have the incline so great there that we begin to slide down the incline. So as we increase the incline, we just overcome static friction enough to get me to just barely move. At that point, our downward weight equals the maximum static friction force. So that's going to be our condition that we're going to start with in order to determine what angle that is. And we're going to get to an interesting point here that might be a bit surprising that we're going to try to prove, in a sense, in class on Monday. But let's do some of our theoretical work first. So first we need to minimize Jeff. You guys don't want to see me this late looking like I do. Ugh, there we go. Here I am back in the corner. What we want to do is draw a force diagram for this object on an incline. So let's draw the incline, right? We have our book. There's our cover, there's our pages, and there's our other cover, and there's the binding, right? So our book is resting on an incline like that. The force diagram, if we are considering the moment just when it starts to move, that's when we have our maximum static friction force, force of friction static. We have our downward weight, and then we have our normal force. Those are the three forces acting on our box. Let's break this normal force as we did Wednesday in class. We can break this normal force into two bits. There's the weight force into two bits. I forgot to label it. That's why I misspoke. There's the force of gravity is our downward arrow. Well, we have the force of gravity in the y direction, and we have the force of gravity in the x direction. Now, I've tried my best to draw this in a way where it looks like the force of gravity in the x direction is about the same size as the force of friction static working against my box, right? Here is that dotted line that represents the incline. And where the y component of gravity is equal to the normal force, because what I'm going to write here is in the x direction, again, same exact process, a much different scenario than we've talked about, but the same exact process. The net force in the x direction is equal to max. Again, we're going to set that equal to 0 because we are moving at a constant speed. When we first overcome the static friction force, right? The static friction force matches our push until it reaches that maximum value, and then we move at a constant speed. And then immediately what happens is kinetic friction is always less than static friction. So if we maintain that force, we start to accelerate. Okay, that's the breakdown of sequentially what occurs. Now, in the x direction, let's say that this is the x direction, because if we do another problem like we'll start class with on Monday, that's the direction where all the action is going to happen. So we can start by saying I have FGX, this guy right here, minus FFS, so the x component of the gravitational force, minus the static friction force is equal to 0. So I have force of gravity times the sine of theta, right? This angle theta is equal to this angle theta by definition, minus the static friction force, which is mu static max, times the normal force equals 0. So again, I'm partway there to answering my question. In the y direction, what do I have? We always think about the y direction when we're dealing with friction. Sum of forces in the y direction is equal to mass times acceleration in the y direction. Well, in the y direction, go back to our force diagram, we had the normal force. Right? If this is positive x, this is still positive y. We have the normal force, and then we have the y component of the weight force. So we have Fn minus Fgy equals ma. Ay is 0 because we're not accelerating off the incline, so the whole net force must be equal to 0. So I have that the normal force is equal to Fgy, which is equal to Fg times cosine theta. So now I can substitute this in over here. I get Fg sine of theta minus mu times Fg cosine theta equals 0. Mg, just a reminder of what F sub g is. Force of gravity is equal to mg equals 0. But I've got, just to be clear on the algebra, let's do the following. I'm going to start a new slide, but I want to take exactly this equation. So some other things might be copied as well. We'll ignore them. There we go. Let's paste that in. The hell with this one. Oh, good. Just the good stuff. So we can solve this. Whoops. Mg sine theta equals mu mg cosine of theta. Mass doesn't matter. G doesn't matter. I get sine of theta over cosine of theta, which is equal to tangent of theta, is equal to mu. So theta is just the inverse tangent of mu. And for this problem, we were told that the mu was 0.45. What were we told? 0.4? 0.45. So we can find for this case, using the inverse tangent, multiplying, or finding the inverse tangent of 0.45, evaluating the inverse tangent, 0.45, we get that theta is equal to 24.2 degrees. The interesting thing is, doesn't matter what the mass of the book is. It just matters the surface is. That's what determines that static friction force. So if I have a light book or a massive book, they will start slipping at the same angle, just determined by the material that the surface of the book jacket is made out of, and the surface that it's sliding on, which is a little interesting. We will try to observe this somewhat surprising result in class on Monday, and then I'll also do the follow-up problem for this just as a refresher of Newton's laws. That's all for our official lecture today, Friday. No in-class assignment. I'm happy if you watch the video. I'm happy if you're keeping up. I'll give y'all a pass on this one. This is important stuff, though. Be sure that you watch this video and follow it along with our introduction to friction. Be sure that you watch the video that I'm going to post tomorrow where I work a few more complex problems, because as you're solving the homework and as the problems get more complex, it really helps to see other scenarios where we're doing the same thing for every problem. Force diagram, Newton's laws. As we get more forces, those relationships get more complex, and it's easy to miss a term or to substitute the wrong term in. That's where we need to be careful in order to get the problem all the way right. I'll stop the lecture here. Very good work, everyone, up to this point. Keep at it. You're doing great. I will see you in class on Monday.